A superatom is any cluster of atoms that seem to exhibit some of the properties of elemental atoms. Sodium atoms, when cooled from vapor, naturally condense into clusters, preferentially containing a magic number of atoms. The first two of these can be recognized as the numbers of electrons needed to fill the first and second shells, respectively. The superatom suggestion is that free electrons in the cluster occupy a new set of orbitals that are defined by the entire group of atoms, i.e., cluster. Rather than each individual atom separately, superatoms tend to behave chemically in a way that will allow them to have a closed shell of electrons. In this new counting scheme, therefore, a superatom with one more electron than a full shell should give up that electron very easily, similar to an alkali metal. And a cluster with one electron short of full shell should have a large electron affinity, such as a halogen. Aluminium clusters. Certain aluminium clusters have superatom properties. These aluminium clusters are generated as anions in helium gas and reacted with a gas containing iodine. When analyzed by mass spectrometry, one main reaction product turns out to be Al13I-. These clusters of 13 aluminium atoms with an extra electron added do not appear to react with oxygen when it is introduced in the same gas stream. Assuming each atom liberates its 3 valence electrons, this means that there are 40 electrons present, which is one of the magic numbers noted above for sodium, and implies that these numbers are a reflection of the noble gases. Calculations show that the additional electron is located in the aluminium cluster at the location directly opposite from the iodine atom. The cluster component in Al13I- ion is similar to an iodide ion, or better still, a bromide ion. The related Al13I2- cluster is expected to behave chemically like the triiodide ion. Similarly, it has been noted that Al14 clusters with 42 electrons appear to exhibit the properties of an alkaline earth metal, which typically adopt +2 valence states. This is only known to occur when there are at least 3 iodine atoms attached to an Al14- cluster, Al14I3-. The anionic cluster has a total of 43 itinerant electrons, but the 3 iodine atoms each remove one of the itinerant electrons to leave 40 electrons in the gellium shell. It is particularly easy and reliable to study atomic clusters of inert gas atoms by computer simulation, because interaction between two atoms can be approximated very well by the Lennard-Jones potential. Other methods are readily available, and it has been established that the magic numbers are 13, 19, 23, 26, 29, 32, 34, 43, 46, 49, 55, etc. Al7 equals the property is similar to germanium atoms. Al13 equals the property is similar to halogen atoms, more specifically, chlorine. Al13X-, where X equals 1 to 13. Al14 equals the property is similar to alkaline earth metals. Al14X-, where X equals 1 to 14. Al23. Al37. Other clusters. Li3 Li equals the 3 interior causes 2 valence electrons from the Li to orbit the entire molecule as if it were an atom's nucleus. VSI16F equals has ionic bonding. A cluster of 13 platinum becomes paramagnetic. A cluster of 2000 rubidium atoms. Superatom complexes. Superatom complexes are a special group of superatoms that incorporate a metal core which is stabilized by organic ligands. In thiolate-protected gold cluster complexes, a simple electron counting rule can be used to determine the total number of electrons which correspond to a magic number via, where n is the number of metal atoms in the core, v is the atomic valence, m is the number of electron withdrawing ligands, and Z is the overall charge on the complex. For example, the O10244 has 58 electrons and corresponds to a closed shell magic number. Gold superatom complexes O2518-, 010,244, 014,460. Other superatom complexes: Ga 233, 2, 11, Al 505, 12.